Hi, everyone, and welcome to the first series of Tools of today. So I would like to introduce our first speaker, Mefta Sadat. So Mefta is a senior ML engineer at Loblaw Digital. He focuses on productionizing ML services, tools, and data pipelines. Mefta will share his experience in setting up a recommender system using MLOps tools like MLflow, Seldon Core, and Feast on Google Cloud Platform. So please give a warm welcome to Mefta Sadat.
Hi, everyone. Welcome to the session. I'll be talking about integrating multiple MLOps tool on the Google Cloud Platform. And yeah, let's start. So I am a senior ML engineer within the machine learning and data platform team at Loblaw Digital. So a little bit about Loblaw Digital and what we do. We are part of the largest grocery chain, Loblaws, in Canada, and we are part of this organization. We have many products, and we operate mostly within the retail and e-commerce space. We have multiple products, including PC Express, which is our online grocery platform. And then we have like Joe Fresh apparel, e-commerce, and PC Optimum loyalty program, and many other products, including micro fulfillment centers and other operations. So in this talk, what we will cover. So our main agenda is to build a recommendation system on GCP and use several MLOps tools and how we set up our ML platform. In our application, PC Express application, when our users logs in, we want to show them a list of recommended products such as this. And this is what we'll be talking about today. I'll give you a brief overview of the whole talk. We'll talk about what are the things we considered when you're building an ML platform on GCP, talk about the machine learning lifecycle in general, and why we are using MLOps, what are the MLOps tools we are using, and our overall platform architecture on GCP. A little bit about the recommendation system we'll be building, and finally I will provide a quick demonstration of everything, how it works in practice, and finally a Q&A session. So let's start with our platform checklist. So when we are building this ML platform, we are thinking about the following set of things, but this item is not only this, but there could be other items as well. So first item here is data warehouse integration. In our case, our data warehouse is BigQuery, where all our data lives, and we want a very tight integration with our ML platform with BigQuery. The next thing is the feature store. So we want to use features. We want to reuse features and store them in a unified manner and serve them for our model training, as well as our model serving in low latency from a database. The next part is the pipeline orchestration. In our case, we use Airflow, and we want to orchestrate different of our machines using Airflow. Then we have model training. So we want to train our model in a scalable and resilient fashion in a distributed platform such as Kubernetes, where we could use things like GPU, for example. And then when we're training all our models, we want to manage them. We want to see how their version control, how they're performing, and for all that we need model management tool. And after that, when we are dealing with the model, then we need to serve and deploy our model so it can be used by consumers. We also want to test our models using some sort of tool, so it's easily testable. We also want to monitor our models in production, how they are performing, or if there is a drift or there is any issue with the model, and we want to look at it or retrain the model. We also need to look at the drift or anomalies that is happening with our data and model performance. Model explainability is also something we are looking at, and how we can understand why the model is predicting something and why it's not. And finally, if our model is not working good, and with the monitoring, we observe this and we want to retrain this model and how we can do it. now I'll talk about the basic machine learning lifecycle. Most of you are familiar with the stages shown in this slide. In typical machine learning lifecycle start with your data. So you have some input data you process, and you make them and transform them in the format you want to use in your machine learning lifecycle. Then you have a feature engineering step where you have some sort of pipelines that you use to feature engineer and store the features in your feature repositories. And finally, then you have like model training. So you select different machine learning algorithms, you experiment, you develop your model. And once that's done, you have the model management part where you evaluate your model, you store and maintain the models. After that, you have a model serving stage where you deploy and ship your model. And finally, the model monitoring where you monitor the performance of your model. In this talk, we will focus mainly on the stages highlighted, starting from feature engineering to model serving. Okay, so why we are talking about MLOps? MLOps gives us the ability to improve the delivery of machine learning models. So you have a very consistent process, starting from design and development of our machine learning application to serving it in production. And MLOps gives us the ability to iterate over our development cycle very quickly. So why do we need actually MLOps? Machine learning life cycles are traditionally very difficult. There are a lot of things involved, and it starts where some data scientist or your researcher would go and experiment things on maybe his Jupyter notebook, and then they will have a model, and finally you want to productionize it and involve other part of the organization. So it could involve collaboration between different teams or different type of engineers, like data engineers or machine learning engineers and data scientists. So they all of them need to know exactly what they're dealing with and what needs to be done. It also involved a lot of different things, such as code. They're versioning different parameters and different artifacts, which is somewhat different than like a typical software development where you only have your code and you test your code. But in our case, you could have data, and you could have different other things that you need to test and make sure they're working as expected. And we also need to monitor starting from your data drift to your model drift and many other things. So what can we do to make this process much better? So we use MLOps tools. The main MLOps tools we'll be using for this are MLflow, which is a model management tool. And then we'll use Feast, which is a feature store platform. And then we use Seldon Core, which is a tool to deploy your models in the Kubernetes platform. Many of you are probably familiar with most of these tools, but I will just go over briefly on each of them, just for folks who haven't got the idea. So starting with MLflow. MLflow is a model management and tracking tool, and it has main components such as MLflow tracking that lets you record and query your machine learning experiments. And it also store your model artifacts and version control your models. So then the next component is MLflow projects, which gives you a unified format so that you can just take your project and run in different environments. And finally, MLflow models is your serialized model that you could just deploy in different tools, such as Seldon Core. The next tool is Feast. Feast is a feature store, and in a Feast feature store, the main components involved are like entities, which is like a primary key to identify a specific feature. And then you have feature, which is a measurable property, like how many orders you are serving in a restaurant, for example, or how many trips your driver is making. And then you have offline store and online store, which are the actual store where you store your features. So offline store is more for your analysis and model training, whereas online store is something you are using to get the features in real time when you are predicting something. And finally, Feast comes with a SDK, so you can interact with different components within the Feast ecosystem. On the right-hand side, you see the Feast architecture. So in our case, our offline store is a BigQuery, and we have a offline store. It is defined as some reference to BigQuery tables and views. You could also set up some queries. And the online store is a Google Cloud data store. So when you run a Feast materialize pipeline, you materialize your features from your offline store to your online store, so they can be served in real time. And when you are model training, you can fetch your features from your offline store easily, and then train your model. And when you're deploying your model, you can actually get the features from your online store. And Feast internally use GCS as a registry, and it also has a repo where you define how your features are organized. The next tool is Seldon Core. Seldon Core is a tool to, like I said, to deploy your machine learning models into Kubernetes platform. It containerizes your applications. It could be your model binary trained with frameworks such as XGBoost, Keras, or TensorFlow, and you could use prepackaged model servers from Seldon Core, or you could use something like a custom Python wrapper or other language wrapper model servers that will containerize your application and you could deploy. So you could have a simple graph like this where you deploy one model and you expose it as a REST API or gRPC. Or you could have a complex graph where you could have multiple models serving in production and routing traffic between them. And you could have A/B tests, you could have multi-arm bandit, and many other things. So now we are going to be talking about the machine learning platform architecture we set up on GCP for this recommendation project. I will first start with our data. So the data warehouse for us is BigQuery. It is also our offline feature store. The first component is the Feast component, which is how we are storing our features. So we have a Dockerized application orchestrated and run in our Kubernetes cluster that is running the Feast pipeline. So the Feast pipeline looks at the feature definitions, and it stores and organizes the features in online store as well as offline store. So when we run this pipeline, our features get materialized from BigQuery to Cloud Data Store so that they're ready to serve. The next component is our model training. So for model training, we write our application in a Dockerized way. So it is containerized and could be run in the Kubernetes cluster. And it can use things like GPU, for example. So it is also scalable. So when we are writing an application, we containerize it, and then we orchestrate and run this application using Airflow, and it submit the model training job into the Kubernetes platform. So when the model training job is running, it's interact with MLflow tracking server, which you also install in the cluster. So MLflow tracking server gives you a REST API to interact with, and it has a model registry, which is a unified model store in Google Cloud Storage. And it also has a backend database. In our case, it's Postgres, but you could have something like Cloud SQL as well. So in this database, it stores the metadata about your model. So when you are training the model, it would interact with MLflow, store your models in model registry, and you can also store the metadata in the database. Finally, when we trained our model, we have all the features materialized in our feature store, and we are ready to deploy. So then we containerize the Python wrapper for Seldon Core. We want some custom flexibility, such as with Feast. So use the custom Python wrapper. And we containerize our model serving application and deploy it into the same Kubernetes platform. When we are deploying this model serving application, it's loading the model from the model registry in Google Cloud Storage. And it is also loading the features for a specific request in real time from the online feature store, the Cloud Data Store, and using these features to predict and serve the response back to the user. The Seldon model server also comes with tracking your metrics, so such as latency, throughput, and other things that you could emit to Prometheus and have Grafana dashboard set up. And we're also logging to Stackdriver. Yeah, so that's the way we set up the platform architecture on Google Cloud. So now I will talk about what we are building. So it's a recommendation system, and in a recommendation system, we want to predict what are the items that a user will be interested in. So you could think of it on the matrix right hand. So you have a set of users and you have a set of items, and have some idea about some of the data, like transaction data about what items the user purchased or viewed or things like that. You have some sort of affinity or preference inferred from this transaction. And our job is to predict the items that we don't know about for a specific user. So we build a product recommendation system. In our case, we use the LiveFM Python library. And this library, you can check it out on GitHub. It's a pretty cool library that also have support for using the core start use case. So when your model doesn't know about a user, but it knows about some of the user features, it could handle the prediction for those users. So it's kind of a hybrid approach. So you have some purchase data, and you also use some user and item features. Yeah. So once we build the model, we are ready to predict and deploy. I found these two articles online that gives you some idea about how we train the model. And the scope of this presentation is mostly focused on the tools, but not on the model training part, but you can check them out. So I will give you a quick demonstration and how we have everything set up in practice. So in this demonstration, I will show you a different step, starting with first we'll look at the data and different features, and then we'll see how we are orchestrating our feast pipeline to sync this feature into data store, and how we are training the model and building the model in the Kubernetes platform, and finally deploying the model to Kubernetes using Seldon Core. And the last step will be how we are going to be testing our model deployed on the Kubernetes platform using a Swagger UI. So yeah, so let's start the demo. Let me share my screen for a bit. Yeah, so if we look at our data sets, it has the data set is transformed into user, item, and some score, which is based on the purchase frequency of the product for a given user. And we have also the title of the product. And then the next data set is the user features. So we have a user features data set where we categorize the user as a meat user, true or false. It represents if the user has purchased meat products from our grocery store. And then we have the item features. Item features include things like the category of the item or some tag, like such as baking in this case. So these are the data set, and we train the model from one of our stores and use some data from that store. Okay, so the next part is I show you how we are organizing different components. I'll start with Feast. So we have a feature repository defined here. So our feature store is in GCP, but you could also use it local if you're testing locally. And you could use things like Parquet files as your offline store and SQLite as your online store. The next part is where we define our features. Like I show you, we have one user feature that we are defining, and our source is BigQuery, and then we define the user's ID as the entity, and we have the feature view, which is like an object collection of different features. Yeah, so next part is how we run this. So I orchestrate this using Airflow. So we have an Airflow DAG where we orchestrate a Kubernetes workload using this tag. And when it runs, it materializes features from your offline store to your online store. So you can see like we have 30,000 features that are getting synced into data store from BigQuery and now ready for serving. The next part is the model training. So in the model training part, I'll show you how we are training the model. So in our case, it's just a simple Python script where we are training the model using the LiveFM package. So we start by creating some data and then format and transform the data and finally go into the model training step, where we feed a model, we set up the hyperparameters, we give it the input and data sets, and then we train the model. After the model training is done, we then use MLflow to log different parameters, our metrics, and also the model artifacts. So you can see here in MLflow, this is our experiment. We are building this recommendation application, and every time we're running the model training job, we are actually logging all the metadata, different parameters we are using, and the accuracy metric, like area under the curve. So now that we have a model with a good accuracy number, we want to deploy this model. To do that, we get the model artifact stored here in GCS. We select this artifact, and we are ready to deploy this into the Kubernetes platform using Seldon Core. To do that, I will go to our model serving application. So we created a custom template for Seldon Core, so we don't have to deal with YAML files all the time, and we use this template and reuse some of the functionalities. Like I said, we picked that model and we just define this as an environment variable, and as soon as we deploy this code to our version controlling system, GitLab, it starts CI/CD jobs to deploy this into the Kubernetes platform. And in our model serving application, the important thing to note is just we focus only on these predict methods, and we just implement how we are predicting. So in our case, we just use the model, we load it at the load step, and then once the model is loaded, we get the input user ID, we check if the model actually can predict or if it's a cold start case. If it's a cold start case, it will then query feature store, and it will get the features from data store in real time and use that to predict the user's recommendations. So yeah, so once we are deployed, now I'm just forwarding my kubectl port forward from my local to our Kubernetes platform. And now I can test it locally, how my model is doing. I will go to the Swagger editor, and I can test the model. So this is a user ID and input to our model serving application. So I'll pick, let's say, user from here, and then I'll try to predict for this user. And it predicted a list of products for this particular user. Now we will look at a different case where the model doesn't know about the user. So we go and select this user, which is meet user true, but this model doesn't know about this user. So then we will try to predict the recommendation for this user. So as you can see, we got some recommendations. Yeah, it's predicting ice cream, which is good. It's sunny out there. We also see it's predicting bacon because this is a meat user. Now, if we look at the logs, we can see how everything works. Yeah. Yeah, so this is the user we just predicted. So the model doesn't know about this user, and it's querying fast. So we find that from online data store that this user is a meat user, and use this user feature to predict recommended items for this user. So yeah, so that's pretty much it. And now I will be taking some questions.
So yeah, thank you very much for this insightful talk about your experience. So we'll open Q&A. So don't hesitate to ask your questions in the chat, and then I will ask them directly to to Mefta. So I've seen also a few questions about a GitHub repo. So people are asking basically whether you have a GitHub repo available with some parts of your code. I don't know whether that's something you want to share or something that's available. Yeah, that's exactly, we have again the same question. So can you please post the code to GitHub and share with us? Is it something that's doable?
So I shared some of the model training code based on some of the tutorials I followed in the slides, but I don't have a public repository set up for this specific project, but I could take it offline and share something, yeah.
Okay, and there will be access to the presentations later on. So I have a question from Bishan Bang. So MLflow serving vs Seldon serving, any difference, Mefta?
So you could also serve your model using MLflow server, but in our case, there are two reasons we didn't use the MLflow server and use the custom server. First reason is we wanted to integrate some of the custom capabilities, like, for example, Fist. So we are querying the data in real time using Fist. And the second one is the startup time for MLflow server using Seldon Core. We find it a little bit slow. So it will take a little bit more time to start up the container than a custom Python server.
And then we have a question concerning times aspects from Luz Pironello, who's asking, how often do you retrain the models during the day or week? And also, what metrics do you use to determine the retraining periods?
Good question. So it depends on the use case. So one of the use case could be you train your model totally manually. So look at and observe metrics and monitor your model. If it's not performing well and there is a drift, you retrain your model. The other use case is you just keep retraining your model on a schedule because you want to include new products and new users and train for them. So we have both use case in our organization where we have projects where we retrain even daily and or even like weekly. So yeah.
Retraining periods determined by the type of inbound user data?
So they are determined mostly by the metrics we are observing. So if we notice a drift, we are triggering retraining jobs, or it could be based on just to freshen up the model over time. So it could be on a schedule. Yeah.
Okay, great. And then we have a question about the model itself. So I believe we are in collaborating filtering methodology. And so Gandhari Wadal is asking a question about deep learning. So do you use any deep learning models for recommender systems, and do they make any difference?
For us, so far, we have most using the matrix factorization type recommendation systems, but we are using deep learning in other projects extensively. But for recommendation system, we are mostly using matrix factorization.
Okay, so in the LiveFM package you're using, do you know a little bit more about the matrix factorization methods that are used in that package in particular? Or the classical one?
I didn't dive into the LiveFM package specifically, but I know they support a different set of neighborhood-based and matrix factorization-based recommendations. Another package I would recommend you can check out is the implicit Python package for recommendation.
Makes sense. And so what is, Bishan Bang is asking a second question is, what is the approach you use for serving? And can you please share some high-level details, like is it Flask, GUnicorn, when you say the custom Python server?
So we use the GUnicorn worker for our model servers, and we found that with GUnicorn, it's performed way better. Yeah.
And then there is a question from Marco Filippone about the feedbacks. And so basically, do you collect, when you make your prediction, do you collect some feedbacks, and how do you integrate that information?
Good question. So for us, we collect the feedback using our data, and we have a feedback service set up that collects this feedback, and we just use this feedback from BigQuery and build dashboards on top of it to things like monitor performance and other things. Yeah.
Okay, great. And then there is a question from Marco Filippone about the feedbacks. And so basically, do you collect, when you make your prediction, do you collect some feedbacks, and how do you integrate that information?
Good question. So for us, we collect the feedback using our data, and we have a feedback service set up that collects this feedback from BigQuery and build dashboards on top of it to things like monitor performance and other things. Yeah.
And so are these feedback directly re-included in the training models, or are you used it to basically not directly refit your model, but like basically iterate on your model somehow?
Yeah, to iterate on our models. And there is also a way you could use the feedback in real time if you're doing a multi-arm bandit using Seldon.
And we have an interesting also question about the metrics that are used to assess the models. And so what type of metrics? Seen some continuous values. Are we talking about precision because we have this case selection, or what is the metrics here in your system?
There are many metrics used by our data scientists that they include things like precision, recall, area under the curve, or your normalized distributed cumulative gain, discounted cumulative gain, things like that. Yeah.
Okay. Another question from Ryerson Bang. So what is the overall response time under load for your predicting serving?
So our services run under like 50 milliseconds, and we have a lot of requests coming in depending on the service. For example, if it's search, there are hundreds of requests coming in. For recommendation, probably the throughput would be lower, but the response time is in milliseconds. Yeah.
Okay. So let's a few additional seconds in case there is any last remaining question. Anyone else? No. Well, I think it should be. Oh, yeah, we have a question. Okay, so Zach Rosenberg is asking, do you have thoughts on Vertex AI?
Yeah, so that's something we are exploring right now. So we are going to be building the same application using Vertex AI and kind of compare how they perform. Yeah, and if we can use them together as well. Yeah.
And then Vithani is also asking whether you could maybe share a little bit more details on Feast, especially like on Feast you used for offline or online. Could you just share a little bit more details on the tool?
Okay, so what kind of details are you looking for? Are you talking about how you set up Feast, or it's if you can elaborate? Okay.
Yeah.
So for Feast, yeah. So we set it up like a feature repository where you could go in and define your features, and once your features are defined, we can have a pipeline that could run to materialize these features. Otherwise, normally we used to have like data engineering jobs, such as things like data flow, doing this type of feature engineering and loading data. But with Feast on GCP, it comes with the support of materializing the features. So we don't have to spend much time on the data engineering side, and we could do things like join, and it have features like on-point join. So it would have smartly join different features based on the timestamp, for example. So I find that very useful. Yeah.
Okay. So I will then take this last question about Feast. So you used Feast out of the box, or do you use BigQuery or Data Store?
Yeah, so Feast since 1.10, they support on GCP, Data Store, and BigQuery natively. So we use that.
Okay. Well, I think that should be all for the questions. So on behalf of the TMLS team and everyone here, I would like to thank you, Mefta, for that's amazing and insightful talk. So I hope you all have a great day and see you for the next talk. Thank you.